Welcome to Study Loop.
This is the answer to Chapter 13, problem number 40 from the Smith Organic Chemistry textbook. And so this problem is giving us 6 pairs of molecules and asking us to identify what the differences would be in their IR spectrums. And so for A, we have a cyclopentene versus this alkyne. And so the cyclopentene is going to show a carbon-carbon double bond at roughly 1650 and a C-sp2 hybridized hydrogen, so a sp2 hybridized carbon hydrogen bond. And so that's going to show between 3000 and 3150. The alkyne is obviously going to show the carbon-carbon triple bond at 2250 and the CSP H bond at 3300. For B, the main difference in these molecules is that the first one, the carboxylic acid, is going to have that OH bond. And remember, in a carboxylic acid, it's hard to say exactly where that will show, but it will show above 3000 wave number. The second molecule for B does not have an OH bond in it, and so there should be no signal above 3000. And so that makes that pretty straightforward to identify. Moving to C, C is also very straightforward. There should be the distinctive ketone signal in the first molecule at around 1700 wave number. The second molecule in C should show a carbon-carbon double bond at about 1650. The CSP2H bond, again between 3000 and 3150, and the OH bond. And this OH is not a carboxylic acid, as the one in B was, and so we know it should show between 3200 and 3600 wave number, and it should be a nice broad peak. For D, the second molecule in D has a carbon double bonded to an oxygen. So again, we should see that right around 1700. And the first molecule in D doesn't have a carbon double bonded to an oxygen. So again, that's very straightforward to identify. If we were given an IR and knew that it had to be one of these two molecules, we could look right at 1700. And if there's a peak, it's the one on the right. And if there's not a peak at 1700, it's the one on the left. So moving on, E. So in E, this first alkyne is symmetrical, and so we're not going to see the carbon-carbon triple bond signal because the molecule is symmetrical. But for the second molecule in E, we will see the carbon-carbon triple bond, and so that should show at 2250, and the CSPH bond should show at 3300. For F, again, we're looking at how to distinguish these two molecules. And so the first molecule in F has an sp3. The first molecule in F has an sp hybridized carbon bonded to a hydrogen, which will show at 3300. And the second molecule in F does not have an sp hybridized carbon bound to a hydrogen. So there will be no signal at 3300. And that's how you differentiate them. And this is, as far as experimental organic chemistry, this is one of the main uses of IR. If you know what you should have, what functional groups should be there, it's very straightforward to look at an IR and see if the signals are where they're supposed to be. And so that's sort of what we use this for in industry a lot of the time. And so that is the answer to Chapter 13, problem number 40.